So, welcome back student to the next class of complex analysis. In the previous class, we started the Cauchy's residue theorem. Cauchy's residue theorem, where we find that we can evaluate this integration with the form this. So, I can eventually find out the integration of the function fz, which is analytic in a region except few points, which we call this zk, say z1, z2, z3 are few points, finite number of points where the function is not analytic, but still I can evaluate this function if I able to find out the residue at that point of this function multiplied by 2 pi I. So, we have already applied this formula to different problem. So, our aim here is to do more problems. So, today we will like to do more problems in board. So, let us take another example or another problem. The function is given as z e to the power of z divided by z square minus 1. This is the functional form that I have, and also we need to define the domain over which I am calculating that. So, the domain is defined as mod of z is equal to 2. So, as usual, let us try to find out where the domain lies, I mean where this singularity lies for this domain. So, mod of z equal to 2 means I have a circle of radius 2 like this, center at z equal to 0, and now this point the singularity at, so where z square minus 1 is 0, we have the singularity. So, obviously, one singular point is 1 and another singular point is minus 1. 1 and minus 1 are the singular point. Singularity lies in this particular point. So, 1 minus 1, if this radius is 2, then 1 and minus 1 is eventually this point and this point. So, in this example we find that both the points 1 and minus 1 are inside the region. So, I need to calculate the residue for this both these points. So, let us try to do the thing. So, this function, I can write this function as this, and the result is something like, so first we calculate the residue of this function at point 1. So, it is nothing but limit j tends to 1, z minus 1, z e to the power of z divided by z minus 1, z plus 1. I am doing all this thing meticulously so that you can understand, but when you are familiar with this system you can do readily. I mean you do not need to do these steps, you can directly find your result. So, here when this point will going down, I mean this z minus 1, z minus 1, this term will going, I mean they will cut, and then z tends to 1, I just put z tends to 1. So, it will be e to the power of 1 divided by 2. This is my first residue at one point. So, I need to calculate the residue of f at -1 point, because -1 point is also inside the circle. So, I need to take care of that residue as well. So, z tends to -1, I will need to multiply it by z multiply z plus 1 z e to the power of z divided by z minus 1 z plus 1. Z plus 1 will cancel out. Now, I put this value. So, it will be for z I have -1 e to the power of -1 divided by this I put, so it will be -2. So, I will eventually have e to the power of -1 divided by 2. This is my first residue, this is my second residue, one is e to the e divided by 2, another is e to the power -1 divided by 2. So, now just the next thing is just to put this value, that is all. So, the value of integration is 2 pi I summation of residue f z I. So, here it is 2 pi I, the first residue is e divided by 2, second residue is e to the power -1 divided by 2, like this. I have already got the result, but I can modify that. So, this quantity e to the power is something. So, 2 pi I e plus e minus 1 divided by 2, this quantity is cos hyperbolic. So, it is 2 pi I cos hyperbolic of 1. This is the result we have. This is the most closed form we have. So, the function is given, the integration we need to do for this function, the region is given, which is Z2, need to find out where is the point where we have the singularity, then calculate the residue, and rest is straightforward. So, after having this, let us go to some other example. So, another example I have in my hand is integration of 1 divided by z minus 1 and then z plus 2 whole square dz. This is the function. I need to integrate over some circle closed loop C, and the circle is given as mod of z is equal to 3. So, mod of z equal to 3 means I should have a circle with radius 3. This is a circle with radius 3, where the singularity, so singularity first let us find out. Say Z1, one singularity is at 1, this is for simple, this is a simple pole. Singularity Z2 is at Z2 equal to -2, but this is of order 2. Order 2 singularity. So, both the singularity are inside, because one is 1. So, somewhere here and another is 2 somewhere here, -2 somewhere here. So, one point is here and another point is here, both the singularities are inside the circle. So, we need to calculate the residue for both the singular points. Okay, so, let us first find out the singularity. So, residue f at z equal to 1 point, which is limit z tends to 1, z minus 1 divided by z minus 1 z plus 2, square of that. Z minus 1 cancel out. So, I will get this quantity if I put z equal to 1. So, it will be just 1 divided by 3 square which is 1 divided by 9. So, first residue I find is 1 by 9. So, let me write it here somewhere. So, residue 1 is 1 by 9. Now, I am going to find out the second residue, this quantity. This is of order 2. So, residue of the given function at minus 2 point, which is, according to our formula, I should write 2 minus 1 factorial d of dz. I need to write the limit also. So, it is under limit. Okay, the space is not sufficient. So, let me write it once again from here. So, residue f at minus 2 is something like limit z tends to minus 2, 1 divided by 2 minus 1 factorial, which is 1, d dz of z plus 2 whole square multiplied by the function, which is z minus 1 z plus 2 square of that. So, this quantity will cancel out. I need to do the derivative of this quantity. So, if I do, then so it is limit z tends to minus 2. If I do the derivative, it will be 1 divided by z minus 1 square of that with a negative sign. So, minus of 1. Now, if I put it here, this value if I put, then it comes out to be, this quantity is minus of 1 divided by z I put minus 2. So, it will be just minus 3 whole square. So, it is minus of 1 by 9. The same value I got here, residue 1 was 1 by 9. In this case, however, I find it is minus 1 by 9. So, now obviously, you can understand, I believe I am not making any mistake. So, obviously, you can find that this case the integration will going to vanish, because the residue of 2 points are exactly same and opposite. So, that means the value of this integration is 2 pi I sum over residue of this function at I, here I 1 to 2, just 2 residues. So, it is 2 pi I, first residue is 1 by 9 and second residue is minus 1 by 9, and we have a result 0. It may be possible to have this result 0, I mean it is not an analytic function in this region, that is for sure, but still I can get that for some so one residue and another residue exactly balanced to each other, and one can still get 0 result out of that. Okay. So, next example, I should go with another example. Okay. So, it is interesting. So, the function that is given to us is z cube e to the power of 1 divided by z square dz. This is the expression that is given to us, and we need to evaluate it in the region mod of z is 1. Mod of z is 1. So, mod of z is 1 means I need to evaluate this integration for a circle of radius 1. This is a circle of radius 1, and now we need to first find out where is the singularity, where the singularity of this function. So, obviously, at z equal to 0, the function, whatever the function f z, where f z is this entire quantity. So, f z is zq divided by e to the power 1 by z square. This is the function that is given to us. So, at z equal to 0, this function has singularity, and this singularity is essential singularity, because if I expand this at z equal to 0, the function f z has an essential singularity. Now, if the function has some essential singularity, it is difficult to find out the residue in our standard form, because no way we mention that what happened if there is essential singularity. For example, in this case we have some essential singularity, but our goal is to find out the residue. So, residue is nothing but residue of a function f z around some point is nothing but some point z 0 is nothing but, if I expand this function in Laurent series, once again I am reminding you these things because it is important, that should be in your mind, that the residue is nothing but the coefficient of a minus k, that means the coefficient of z minus z 0. So, this is my residue. So, I need to find out this. So, if somehow I can able to expand this function in Laurent series and take out this coefficient, then I am done. Then I can calculate the residue without doing all this recipe, without, for example, here the recipe will not going to work. So, in that case, so let us try to find out whether we can do a Laurent series expansion of this function or not. So, this function I can write it as zq e to the power of minus 1 by z square. The singularity is here, sitting here. So, now I will going to expand this function. First term will be 1, second term will be minus of 1 by z square, third term will be plus 1 by z cube, it is square, mind it. So, it will be z to the power 4 of factorial 2, third term will be minus 1 divided by the cube of this term. So, it will be z square whole to the power cube. So, it will be 6 factorial 3 and so on. This will be my series. And now, if I do the calculation, if I now simplify this, first term will be z cube, because this is the expansion of e to the power 1 by z square, that is the expansion, but I am trying to find out what is the expansion of the full function f z. So, z cube is the first term, second term will be z, third term is interesting, which is 1 by factorial 2 and then it is z, and fourth term is minus 1 by factorial 3 and then z cube and so on. So, this is exactly the Laurent series expansion that we have. This part is your analytical part, this is analytic part, and this rest part is your principal part. And we know that the residue is nothing but the coefficient of z minus where the singularity is. So, here the singularity is z equal to z 0. So, that means I can write this expression in principle in this way, z minus 0 cube minus z minus 0 and then 1 by factorial to z minus 0. So, that means my residue is coming out to be half. So, my residue here for this case, residue is coming out to be half. So, once I find out the residue, the rest part is straightforward. So, the rest part is this, that means the answer of this thing is 2 pi I multiplied by residue of this function at z equal to 0 point, which we evaluate there. So, 2 pi I multiplied by 1 by 2, which is pi I. So, this is the solution we have. So, this is a different kind of example, and I put this example so that you can understand that always it is not necessary that you will use the standard recipe to find out. Always it is not necessary that you use the standard recipe to find out your residue. Rather, sometimes you need to use the expansion, and this expansion sometimes helps. Okay, next problem is something again of interest. So, the function is given like this. This is the function, and I need to evaluate at this point. Right. So, again we need to find out where is the region, where is my region. So, the usual process to find out the region. So, this z minus 1 means I have point 1 here, and having radius 2, if I draw a circle of radius 2, then it will be something like this. So, this point is my minus 1, this point is plus 1, this point is minus 1. So, that the radius is 2 and this point is 3. Okay. So, this is my center, this point is 3, this point is minus 1. Okay, I know the region. Now, I need to find out where the singularity lies. Obviously, this first singularity lies as z equal to 0 point, it is a singularity. Z equal to 0 point, we have a singularity. Apart from that, any other point where you have the singularity? Yes, at z equal to pi by 2, we have singularity, at least which is inside this. So, pi by 2 also minus pi by 2, I should have an singularity, right. Minus pi by 2 also we have some singularity. I am checking where I am getting the singularity, minus pi, pi by 2, and the odd multiple of all these quantities seems to be the singular points. Now, the question is pi by 2 and minus pi by 2, where they are situated in this. So, pi by 2 is around 3.14 divided by 2. So, it is roughly 1 point something, it is greater than 1, obviously it is greater than 1, but obviously less than 3. So, it is, if it is greater than 1 and less than 3, so obviously its location pi by 2 is situated somewhere here. So, this is my pi by 2 point, which is inside, What about minus pi by 2? Minus pi by 2, obviously we will have a minus here. So, it will be something 3.1 by 4 by 2, and which is again less than minus 1. So, that means this point is just outside here. So, this point is just outside here, minus pi by 2, just here. So, I can exclude this minus pi by 2 point. So, now I know where is my singularities, and all the other points will be outside, at least for this given, and now we are ready to calculate the residue. So, let us first calculate the residue at z equal to 0 point. What is the residue we will have? So, residue of this function at 0 point is limit z tends to 0, z multiplied by the function, which is limit z tends to 0, z multiplied by tan z divided by z. So, z will cancel out. So, what we will get if I put the limit tan 0 is 0. So, my first residue gives me the value 0. My first residue gives me the value 0. What about the second residue? So, residue of this function at pi by 2 point. So, I need to multiply limit z goes to pi by 2, I multiply z minus pi by 2, and then this function I write as sin z divided by z cos z to make it convenient. Now, at z equal to pi by 2, here we can find that pi by 2, when I put z equal to pi by 2, this portion is 0 and the downstairs is also 0. So, 0 by 0 form. So, again I will use this L'Hopital rule, and if I use this L'Hopital rule, then I need to so derivative of this quantity. So, first derivative of this quantity, that means it is 1. So, sin of z plus z minus pi by 2 cos of z, and the downstairs we have first is cos of z and second is minus z sin of z. Now, if I put the limit, there will be no problem. If I put z equal to pi by 2, this quantity vanishes, but this quantity stands. So, I will finally have sin pi by 2 divided by cos pi by 2, which is 0, but minus pi by 2 sin pi by 2. So, eventually I will have minus of 2 by pi. This is my residue. So, first residue is 0 and my second residue comes out to be minus 2 by pi. So, this residue is minus 2 over pi. So, what will be the value of this integration? This integration is 2 pi I summation of residues of function evaluated at different. So, here we have 2 pi I, first residue is 0, but second residue I have some value which is minus 2 by pi. So, it is eventually minus of 4 I, this is the result. So, pi will cancel out, 2 is there, minus, okay. So, minus of 4 pi. So, well student, I would like to stop the class here. So, today we will mainly cover different kind of integral problems and find that the Cauchy's integral form Cauchy's residue formula can be used to figure out the function if the contour is given to you, and you can evaluate different kind of integration without doing that, just using this residue theorem you can evaluate that. In the next class we will show some consequence of this Cauchy's integral formula, whereby exploiting this Cauchy's integral formula you can evaluate even the real integrals. So, that is most interesting. The real integral we will going to evolve, we will going to solve by using Cauchy's integral formula. So, with that note, let me conclude the class here. See you in the next class. In the next class will be treated with the fact that we will use the Cauchy's integral formula to solve a real integration. So, thank you for your attention. See you in the next class.